Okay, perhaps we can start. So the last time we talked about reducing matrix to the echelon form. So today we'll continue talking about linear transformations. We'll talk about linear echelon form, reduced echelon form, and solutions of systems of linear equations. So before we go, do you have any questions? Okay.
Okay.
Good. So so let's recap a little bit. Let's start with let's take just take a matrix, reduce it to the echelon form, and then interpret the solution as interpret this as having the linear set of linear equations, right? So in terms of solutions of system of linear equations. So let's take a different matrix now. Let's say it's made of the matrix 3 by 6. By the way, did you download Mathematica? Did you?
I think it costs.
Right. So good. So since it's yeah, like there's a student version you have to pay, but there's a free version if you go online. It's the website is called Wolfram.
Yes, yes.
Yeah. So there you can do the same calculation. So let's take the matrix 3 minus 6, 6, 4, minus 5, 3 minus 7, 8 minus 5, 8, 9, 3 minus 9, 12, minus 9, 6, and 15, like that. Okay. So the right. So the remember we need to identify the first pivot column, and then because of the 0 here, we need to swap lines, swap rows, right? It doesn't matter which rows we swap, so we swap the third one with the first one. So we take the third one, put it up here, and then swap them here. Right, so then we can get rid of the second column, right, by multiplying by -1 the first column, and then subtracting it. We can just subtract the first column from the second column. Yeah, first column from the second column. So we had 0 here. What will be here?
What?
What will be this answer equal to?
So how 3 changes into 0? I missed it.
Oh, sure. So we multiply the first row by -1 and then add it to the second row.
Oh, okay. I know. Okay. So 2.
Mm-hmm.
-4.
Mm-hmm.
4. 2. And -6.
Yeah, okay. Right. So now the next pivot position is this 2. Right. So we need to sort of can make immediate simplification, right? If we you can see that in the second row, all numbers are even, right? So we can just divide them by 2. So that will make things easier. Right, and now let's get rid of the third column, the third row. And so multiply the second row by -1. Okay. We'll multiply the second row by -1, sorry, by -3, -3, right? And add it to the third one. So we get 0. What's here?
0.
Yes.
And 0.
Okay.
1. And 4.
Mm-hmm.
4.
Yeah, that's right. So yeah, so now it's in the so-called echelon form, right? It looks like a staircase, but it's not the reduced echelon form yet.
Yes.
Okay, so what do we do now? We need to get rid of these numbers and that number.
Yes.
Okay, so let's keep going. So now we're doing the backwards backwards operation. So yeah, so here the
multiply the second row by 9 and add to the first row.
Oh, you want to do this one first?
Yes, both are okay.
So it's actually, I think it's better. So it's better to start from the bottom to the top. So first we get rid of.
Okay.
So let's multiply the third row by -1 and then add it with the second row.
Okay.
So we get 0, and here we get what?
-7.
Sure. And then so now we need to kill the 6. So instead of 6, we'll put 0. What would be instead of 15?
-9. Yeah.
Yeah, that's right. So that takes care of this. And then here, see, if we did what you suggested first, right? So then this number will still change again, right? So, but now with 0 here, so we don't have to worry about these numbers anymore.
Yes. And
so
we can divide by 3 for the first row.
Oh yeah, we also need, right, so good. So let's divide by 3, so it's 1 - 1, 4 - 3 - 3, and now we can add the second row to the first row, right?
Yes.
So that will give us, it's going to be 0, and then here's 2 -1,
-10. Yeah. Can you hear me?
Yes, I can hear you. Yes.
Is there some noise?
Noise. Is it better now?
Yeah.
From the laptop. That's one sec. I usually do it with the desktop, but somehow let's see. It might go away. If no, then I'm just gonna restart. Doesn't take that much time. So okay. Let's see. So I hope it will go away. If not, I'm just gonna switch the machine or restart this.
Okay.
I'm just checking with my nose. So it's going to be 4 - 7. Yeah. Okay. Good. So right. So now this is the this is the system of equations in. So now we have reduced it to everything fine. So we have reduced it to the echelon form, to the reduced echelon form. So we have all ones are pivot points, right? And then it's a staircase, and also all columns have all pivot columns have only one at the position of the pivot number, and the rest as 0. Okay, now. So remember that this matrix, we can think of it as an augmented matrix for the system's linear equations. So there's a matrix A, and then you can multiply it by vector X to get vector B. Right. So and the matrix A here is given by this submatrix. So this is A. So you told me last time that you know how to multiply matrices, right? So
yes.
Right. So and yeah. So now it's a 5-dimensional. There are 5 vectors. Vector X has 5 components. Right. So it's so those components are X1, X2, X5, right? And then when you take this matrix, right, you multiply it by this vector, you get a row, right?
Yes.
Actually, a column, right? So and the equation tells you that this column is equal to the column vector 0, 0. Excuse me, minus 10, minus 7, minus 10, minus 7, 4. Right. So if you take it here, so the equation tells you that B is equal to this. Right. So sorry. So this is the equation, right? AX equals to B, and we can write it if you move it to the left-hand side. It will look like this, right? So that this is equal to this is equal to 0. Okay, but again, we'll not write it in a standard form. So let's do the matrix form. So we have the So we'll do it like this. Sorry, and now. Going to write the solution here. So there are 3 equations. So this is equal to minus 10. This is equal to minus 7. And this is equal to 4. Right. So we immediately get the solution for x5. Right. So x5 is equal to 4. And then for the remaining 4 variables x1, x2, x3, x4, we have 2 equations, right? Which means that they're not fixed completely, so that there are infinitely many solutions, right? So it's up to us to decide which of those variables are parameters, and which of those variables are can be found from this equation. So out of 4 variables, we have 2 equations. So there are 2 parameters, 4 minus 2, right? And 2 other variables can be found using these 2 equations. Now, there is a we can so there is some ambiguity in this in deciding which variables are parameters and which are determined by the equations. So let's adopt the following rule, right? So if you have a matrix of the pivot form, in echelon form, then x5 will be the variable. So x5 is the variable. Now x2 is the variable and x1 is the variable. So we're looking at pivot columns, right? So column 1 is pivot column, column 2 is pivot column, and column 5 is pivot column.
Yes.
So 3 and 4 will be parameters here. So x3 and x4 are 3 parameters, right?
Yes.
And then we can find, we can solve the, for example, the first equation. We can find x1 from the first equation, right? And we can find x2 from the second equation. So we solve this for x1. That gives us minus 10 minus x3 plus x4. So let's collect the solutions, right? So we know that x5 is equal to 4, x3 and x4 are 3. And this equation was solved with respect to x2. So that's x2. Oh, sorry, x1, excuse me. Yeah, so what have I done? Sorry. Yeah, so so this is all with respect to x2. Okay, so let's put the solution together. So x5 is this, x2 is that, and this is all with respect to x1. X1 is this. Yeah.
Yes.
Okay. So what is the set of solutions of this linear system of equations? Well, it is a two-dimensional space, right? It's a space. It's a set that is parameterized by two parameters which are completely free. So x3 and x4 can vary between minus infinity and plus infinity, and they can take any value.
Yes.
Right. So yeah, which is expected, right? Because you have less number of equations that than the number of parameters. Okay. Now, perhaps let's look at an example. So now I'm often, yeah, so remember, yeah, we talked about this sort of we classified all possible cases when we have a solution, or we have solutions, so there may not be a solution, right? So the solution may not exist. And we can try to understand what this means in terms of this echelon form of the augmented matrix. Right, so see here, we had an augmented matrix like this, right? And its last row was 1 and 4. And so from here, we immediately decided that x5 is equal to 4. Okay.
Yes. Yes.
Now, imagine that instead of this 1, you have 0. Right? It's not this example, but some other example. Imagine you have 0 here.
No solution.
Then there is no solution. Yeah, that's right. So therefore, you can make a statement that the system is consistent, meaning that it has at least one solution if the augmented matrix in the reduced echelon form does not have a row like that. So we can look at it here. So a linear system of equations of the form a x equals b is consistent, meaning that it has at least one solution. It has solutions, one or infinitely many. In this case, infinitely many. So if it's augmented matrix in its echelon form does not contain row like a row of the form. I'm going to copy it from here. And then instead of 4, there can be any constant A. Right? So because if it did, then we know for sure that there is no solution. So
Yes.
you can deduce existence of solution just by looking at the reduced matrix. Great. So there's some practical problems that you can do. I hope they'll be very helpful. Yeah. So and I think last time we looked at the problem where at the system of equations which was inconsistent, right? So do you want to do another example, or shall we keep going?
What?
Do you want to look at another example when the system has no solutions?
You mean another example? Do I need?
No, but yeah. So do you want me? We can do it now in class, or I mean, so this example above it has solution, right? So we have a solution here. This one.
Yes.
But if the augmented matrix has this row, then there is no solution.
Yes.
If you want, we can look at an example of such kind. If it's clear, then we should keep going.
It's clear. Clear.
Good, thank you. Yes. Okay. Now let's talk about vectors. I think we want to switch to sharing tablet. Yeah, so that's where we stop. Let's talk about vectors. Right, so what is a vector, right? So let's say vectors in R2 first. So a vector in R2 is an ordered pair of two numbers. An ordered pair, let's say x1 and x2. Right, so here I draw it as a row, right? But in principle, you should write it as a column, right? So so it's an ordered pair, meaning that vector x1 x2 is different from vector x2 x1, right? So it's a different point. So we can add vectors together. So we can add vectors together. So there are some operations that are allowed on vectors. Right, so if you have vector x, say with an arrow on top of it, because if you read the book or if you or paper, people use the bold font, right? So instead of drawing vector, they would just draw the bold letter, but it's not so convenient to do by hand. So we have two vectors x, which is x1, which has components x1, x2. Yeah, so this numbers they're called components of the vector. Components of vector x. and if vector y has components y1, y2, so you can add them. And in fact, you can add them with some coefficients, right? So you can take coefficient alpha and add vector y with coefficient beta, right? And that will give you the vector for the following components. It's alpha x1 plus beta x2, alpha x, beta y1, and then it's alpha x2 plus beta y2. So in other words, when you multiply the vector by a number, and here alpha and beta are real numbers. So this is the, I remind you, this is the sign of a set of real numbers. So this property is called linear property. So for example, if you have 10 times vector 0, 5 plus 7 vector minus 1, 0, what will be the vector? What will be the components of this vector?
-7 and 50.
Yep, sure. That's good. Okay. So there's no problem with that. Now, there's a convenient presentation of vectors as using the coordinate plane. If you talk about R2, right? So if it's x1 and x2, so the pair of the order pair x1 and x2, they provide us the position of a point with coordinates x1 and x2, right? So like it's a point over here with coordinates x1 and x2, and the vector that goes from the origin to that point, this vector x, will have x1 and x2 as its components, right? So here, vector x looks like x1, x2. So this way, there is a one-to-one correspondence between the set of points on a plane and the set of all vectors in 2 dimensions, right? And that's how it goes, right? So for every point, there's a vector that connects the origin of the coordinate system with that given point. So here it's clear that the pair must be ordered for this correspondence to hold, because if you swap x1 and x2, there will be different point here with coordinates x2 and x1, which will have a different vector associated to it. So it's some other vector, we can call it x tilde.
Right.
Right. So do you know how to add vectors geometrically? Like if you have these 2 vectors x and x tilde, what's the how can you draw vector x plus x tilde?
Yeah, I think there is a rule.
Remember how it's called?
Parallelogram,
right? So
yeah, parallelogram.
It's either parallelogram or the triangle, right? So you need to take the say first vector, and then because remember a vector. So we define a vector as it's a directed segment, right? But we can also we are free to move it up and down. Like, we're not up and down. We can free to move it anywhere in a plane. Yeah. So it's this by vector we think of basically a direction and the length, right? So it's yes. A directed segment of a given length, but its tail or its tip are not fixed. So that this way we can just Yes, we draw. We put X here. And then now we need to connect. Sorry, make a better picture. Connect it diagonally like that, right? So then, so the parallelogram that you were talking about comes here, and this purple vector will show you the sum of vectors x1, x, and x tilde, and it has components. We just discussed it, right? Well, the one that we drew here is x1 plus x2, and here's also x1 plus x2. But in general, if instead of vector x tilde, you would have some vector y, then yeah, you'll have this one. Okay. Now, that's what happens in 2 dimensions. Now, there's nothing should stop us from adding more numbers, right? So we can take sort of we can instead of looking at the ordered pair of numbers, we can look at ordered triple of numbers. So vectors in R3. So let's say there's a vector again, vector x. Now it has coordinates x1, x2, x3. Again, they're ordered. Now we should think of this vector as a you can sort of think as a point in 3-dimensional space. So let's label the axis by x1, x2, x3. And again, you can pick a point. Let's maybe take different locations here. The point P that has coordinates x1, x2, and x3. And of course, the vector that connects from the origin to the point, vector x, will have the same components. And it has components x1, x2, x3. And then same rules of operations apply in 3 dimensions. In particular, if you want to add 2 vectors, you can draw, and now you will need to draw a parallelogram in 3 dimensions, right? It would lie in a plane, right? So you want to add 2 vectors together. The vector x and vector y with components y1, y2, y3. Then what happens? You need to sort of 2 vectors, they always lie in a plane. We'll talk about this today, a bit later. And then you draw a parallelogram like this, right? And then the sum of these 2 vectors will be given by this. So that's x plus y, which has components x1 plus y1, x2 plus y2, x3 plus y3. Okay.
Okay.
And well, I'm out of the page. I need to move up. You got this PDF yesterday, right? I sent it to you. And then, in fact, we can nothing should stop us from talking about vectors in n-dimensional space. In Rn, so first let's talk about this notation for a second, right? So when you say Rn, right, it's set theoretically, it's implied that you take R, and then you make what is known, you multiply it by R. So this cross operation is known as direct or Cartesian product, right? So you do it n times. And what it means, you simply take all possible points from each of those R's and then combine them together in ordered tuple, right? So vector X here corresponds to ordered tuple X1, X2, X3, and so on, Xn. Right, we cannot draw it any longer on the paper for n bigger than 3. However, we can still do operations with those vectors. Right, so in particular, there's a 0 vector, which has components 0, 0, 0, all zeros. And then here are the properties of vectors, properties of arithmetic operations with vectors. Okay, that's somehow I got dropped. The screen disappeared, right? So I'm just gonna list them in some order. So first, the vector addition is commutative. So u plus v is equal to v plus u. So if vectors u and vector v, they belong to Rn. Right, then addition is associative. So u plus v plus w, that's w. So if you add them like this, we can also add them in a different order. Right, so that just follows from the associativity of addition. Right, so then if you add 0 vector to u, you'll get u back. And then there's a vector minus u, right, which is obtained by multiplying -1 by u times u. So minus u plus u is equal to 0 vector. So you probably know the word. So these 3 operations, they give the structure of a group. Have you heard this before? It's a mathematical structure. It's called the group.
No, I haven't heard the
So
group.
what is a group? It's a set which is equipped with an operation. In this case, the set is Rm, and the operation is addition, right? So you can take vectors, you can add them, you get a new vector, right? So this operation was so addition, it takes 2 vectors and give it and assigns it another vector, right? So we take vectors u and v, and that it gives it a vector u plus v, which is also a vector. Now, this operation is associative, right? So the second property is true. Now, there is what is known as the unit element, 0. So it's an element, so if you add this element, that nothing happens. So u plus 0 is equal to u. And also there is an inverse element. So it's an element such that if you add it to your, so for every element, every element u, there is an inverse element. So so that if you add them together, you'll get 0. You'll get the unit. So
yes.
Algebraically, we say that vectors, they form a group under addition.
Okay.
And yes, groups appear in many. Okay, but we can continue the list, right? So that's about multiplication. So if you take a constant, okay, I already wrote in previous slide. Let me just reiterate it here. So alpha u plus beta v what did I want to say? Oh, no, yeah, I want to say something different. So, yeah, let's do it like that. Yeah, so alpha plus beta times u is equal to alpha u plus beta times u. And then alpha u plus v is equal to alpha u plus alpha v. So you can just open up the parentheses when alpha, beta, just some real numbers. Okay, and then a couple of more. Now, here we're talking about multiplication, right? So there's, if you take 1 and multiply by vector u, you get vector u back. And then if you multiply two numbers, so alpha times beta u is equal to alpha beta times u. So there's a different algebraic structure, which is called a module. So the fact that you can multiply vectors by numbers like this, right? And then these two equalities are true. So alpha plus beta times u is equal to alpha u plus beta u, and then the other one. So this 4. It's not part of the curriculum, but I just wanted you to know. So these 4 properties they show you that Rn as a vector space is a module over R. And so meaning that you can take any vector and you can multiply it by a coefficient, and you can add them together. Okay.
Okay.
Oh, and the first, you probably know the name for the first property. So that the order of addition, so the u plus v is equal to v plus u. Do you know how it's called? It's called commutativity. It's the commutativity of addition, right? So that the order of vectors when you add them does not matter.
Okay, I know.
So, well, addition is commutative, multiplication is commutative, but well, as we'll get see, I'm sure we're going to talk about this in this course. Okay, we might. There is something which is called vector multiplication, the cross product, and it's not commutative. It's an operation that depends on the order of terms. So say u multiplied by v is not equal to v multiplied by u. So in mathematics, we don't take this for granted, right? So not every structure is commutative.
Okay.
However, you know, counterintuitive that may seem. Yeah. Okay. So, but otherwise, I hope these properties are self-explanatory. Okay. Our next story is linear combinations. So yeah, it's a concept that's used a lot in the algebra. So let v1 V2, and so on, Vp in Rn, P some be some vectors in Rn, right? And then let C1, C2, and so on, Cp be just some numbers. So sometimes we use the word scalar. Scalar means that it's not a vector, it's a number. So 5 is a scalar, but vector 111 is a vector, right? So any number of sources scalars. Then I'm giving the definition of what linear combination is. Then the linear combination of vectors v1, v2, and so on, vp with coefficients C1, C2, and so on, Cp. So coefficients, and another name for those coefficients is weights. Is the following. Is the following sum. It's the C1 times V1 plus C2 times V2 plus and so on plus Cp times Vp. Right, so you take first vector multiplied by first number, second vector multiplied by second number, etc., and then you sum them up. It's just a name, but it's used quite a lot. Right, so examples. You can any examples to give. For example, v1 plus 5 v2 minus 100 v3. It's a linear combination with of vectors v1, v2, v3 with coefficients or weights 1, 5, and minus 100.
Okay.
So the one more part of the definition. If all C1 through Cp are equal to 0, then this linear combination is called trivial. Right, so just it's equal to 0 vector. Right, so just multiply every vector by 0. That's called trivial linear combination. And then if at least one of those coefficients is non-zero, then it's called non-trivial. Well, at least one of C1 through Cp is non-zero. Then the linear combination is called so we'll use these terms a bit later to describe solutions of systems of equations. Okay, good. We've been talking about almost an hour, so let's maybe take a small break and then come back in several minutes, okay?
Okay.
Yeah, I'll see you soon.
I'll see you soon.
Okay, are you there, Iris?
Yes, I'm here.
Sure. So by the way, I was told by Lucia that some of the students are taking some entrance exam in China, right? So it's like entrance exam to Chinese universities, or or to grad school? What is the?
For the university.
Well, but aren't they already enrolled in McGill or some other place, or?
Yeah, but they need additional grades, so that can prove they are a student in high school. So they finished the high school.
Ah, the high school. Oh, I see. I see. So just some mandatory exam that all students need to take, right?
Yeah.
I see. Yeah. Yes, I think yes. We're not going to do any. Yeah, we're just going to this week. I'm just going to read the lectures and probably do the discussion next week when 2 other students come in. Okay. So let's look at some interesting example of linear combination. Now, I told you here. Neighbors starting the car. So I told you here that the C1 through CP, they are in R, but we are also free to consider some subsets of R. For example, we can take Z integers, right, as a subset of R. So let's look at linear combinations of vectors with integer coefficients. So let's pick 2 vectors. V1, which is equal to, say, 1, 1, and vectors V2, which is, for example, I don't do minus 1, 1. And let's draw them on a coordinate plane. So I could make it a bit bigger. So that's x1, x2. So 1, 1 vector looks like this. Right, so that's 1, 1. It's V1. And minus 1, 1 looks like that. And the linear combinations look like this. We have numbers n v1 plus m v2, where n and m, they are integers. Right? So what, for example, let's look at n equals 1, m equals 2. So 1 times v1 plus 2 v2. Where is this point? So if v2 is here, so we take v2 twice in this direction, so that's 2 v2. And we need to use the parallelogram rule to find the sum. So it will be this point, and then the vector will be like this. So this vector is v1 plus 2 v2. Now let's or one of the coefficients can be 0. For example, we can have some vectors like n times v1 plus 0 times v2. And in this case, we can draw a line which contains v1, right? And then on this line, we'll have equidistant points like this, right? So here will be 2v2, 3v2, etc. And then here on the bottom, we'll have minus V2, minus V1, V2, excuse me, V1. V1 minus V1 minus 2V1 and so on. You got the idea. And we can do the same in the V2 direction. Right, and then we can do it. So you can see, we can draw this. We can have, say, V1 plus any number of V2s, or 2V1 plus any number of V2s, 3. Well, I'm trying to draw them as parallel as possible, but I hope you got the idea. Move them also, and then we parallel lines in this direction. There should be more arrows. Okay. Oops, sorry, I accidentally pressed the wrong button. And so on. So on intersection points of this, so we have a mesh. We have the lattice of points, and every lattice, every vertex, every intersection, every point of this lattice will have coordinates given by this linear combination, right? So if you wish, that V1 and V2 are sort of the new coordinate vectors, right? So we have set up the new coordinate system so that every point in this lattice will have coordinates like this: nV1 plus nV2. And you can draw the vector that connects it from the origin to that point. So interesting fact about this structure is that if you take any two, so you have one point, which is n1 vector, one linear combination, say n1v1 plus m1 v2. Say it's, pick a different color. Say it's this point over here. It should be an origin. So that's n1 v1 plus m1 v2, and take another one. So we want to add another point, which is n2 v1 plus m2 v2. Let's say it's somewhere here. Right, so n2 v1 plus m2 v2. And now we can add them. So to do this, we do just standard vector addition, but we can write it here, right? So let's say it will be n1 plus n2 v1 plus m1 plus m2 v2. And again, by construction, this point must be on a lattice, right? Because if you add two integers, it's an integer again. So the integers are closed under the addition. So if you add these 2 points together, then you get the resulting point will be somewhere here. And here. Right, because the way I do it, n1 is 1 and n2 is minus 1. So, and they'll add up to 0, and then right. Does that make sense?
Yes.
Yeah. So basically, like you don't have to, yes, but you don't have to consider linear combinations with real coefficients. They can be also integer coefficient or rational coefficients or from any subset of R. And then you can even introduce multiplication of numbers this way, right? So let me tell you the story. This is so-called these are called Gauss numbers, which is the integer version of complex numbers. Now, for simplicity, let's orient this lattice vertically, so it will go vertically and horizontally, like this. Right, and then say these are the coordinate axes. Well, we don't have to put arrows in them. And now, the idea that you can, so every point will be, again, it's a linear combination. So let's say we call it Z, which is an integer. So there'll be two vectors. One we'll call, so this is origin. One we call E, and one we'll call I. So every point on the lattice will be integer point. So it will be Z. It will be some combination of n times E plus m times I. And the rule of multiplication is like this: that sort of I times I is equal to minus E, and then I times E is equal to I. So if you want to multiply two numbers, say Z1 and Z2, Z1 is N1E plus M1I, and Z2 is N2E plus M2I, then the product will be like this: so Z1 times Z2. I'll write it down. Then you open up the parentheses. It will be, and E times E is E also, right? So it's just the same. It will be N1, N2 times E. And then when you multiply M1 and M2, we'll get minus sign, right? Because get minus M1, M2, everything times E. And there will be the cross products, N1, N2 plus N2, N1 times I. So this is the real part, and this is so-called imaginary part. So this way, it allows us. So this structure allows us to multiply vectors if we introduce this dictionary. So it's important that square of the I vector, so I times I is equal to minus E. Right? So this system of numbers works like so we should think of the Z is the normal linear combination, so we just add vectors as usual, and then but in addition to this, we can also multiply. So multiplication is the new element here. And then so this is the precursor of so-called complex numbers, where you can do exactly that. So this is how you would multiply two complex numbers, and there is a one-to-one correspondence between the complex number and a point on in the two-dimensional plane. It's basically the same story as I write here. Okay. Oh, we got joined by Sophie. Hi, Sophie. Yeah. Okay. So we've been talking about linear combinations of numbers, and the last story was the detour about linear combination of vectors with coefficients in integers. Okay. Now let's do some more. I think we should now switch back to Mathematica because it's easier to type there. Let's look at some examples of linear combinations of vectors. Say, I'm gonna write the vector here. So you have one vector which looks like 1 to 1 minus 2 minus 5. Call this, say this is vector A. So A1 is this vector. Then vector A2 has components 2, 5, and 6. And vector B has components 7, 4, minus 3. Now, and here's the question: can B be written as a linear combination of A1 and A2? Right. So for this, we need to solve the following problem, right? So we take A, we can multiply by some coefficient alpha, add it vector to A1, then add vector A2, multiplied by some coefficient beta. And then we can ask ourselves, is it true, is it possible to find alpha and beta such that these two vectors such that the system holds. And then we can reformulate this in terms of the linear system of equations, right? So now we can write this as a matrix equation. So if you take the matrix like this with coefficients whose columns are given by these numbers, right? And then we multiply it by this vector, and with coefficients alpha and beta, right? We'll get exactly the left-hand side of this equation. Right, so we know how to add the numbers together, add vectors together with coefficients. That's what we get if we do this. Is this clear?
Yes.
Yes, it is. Right. So now we sort of what we're doing essentially, we're solving the system of equations, system of linear equations, where the right-hand side is given by this vector.
Is that means that alpha could be 3 and beta could be 2 for the to solve this equation?
You already found it, right? Right. Yes. So, you can, yes, of course. Like it's a simple equation. Here you can find indeed. So if alpha is equal to 3, right, and beta is equal to 2, then it works, right? So it's not so hard to guess the numbers here. But for the pedagogical reasons, let's solve this problem by row reduction procedure that we talked about the last time and today. So we'll write the augmented matrix and we'll reduce it to the echelon form. Yeah. So yeah, the answer is correct. So let's find the augmented matrix. So we'll take those numbers here, those numbers there. Okay, and then so Sophie, did you look at our video yesterday? Did you look at the?
Yes.
Do you know how to reduce the echelon form?
Yeah. First step is to times row 1 for 2 and add to row 2.
Yep, that's
so
right.
the first column of row 2 with 0 and 3.
What will be here?
9. 18. 18. Yeah.
And then we can do this here.
Times 5. 5 times row 1 and add to row 3.
Yes, 0, then what will be here?
11. 11.
No, it's 16. Right?
Oh, sorry, 16. Sorry.
And then here.
32.
Yep, that's right. Okay, what we'll do next?
To divide row 2 by 3.
Even by 9, we can do that. Right?
Oh, 9 is okay. Yeah.
Yes,
so it becomes
by
0, 0, 1, 2.
And we can divide row number 3 by
16, 1, 2.
Yes, that's right. Okay, so we see that the two rows are identical. The third one is so we can subtract it.
So yeah.
So what does it mean then? Then the so and then let's also reduce it to the pivot to the let's make it to the reduced echelon form. So let's get rid of these 2. So we multiply the second row and add it to the first row. Right? So that will give us what? 0 and then 3. Right. Yeah. So from here it follows that indeed it's the first pivot column, second pivot column. So it says that alpha is equal to 3 and beta is equal to 2. So here we were lucky that the third row turned out to be 0, right? So for example, if you change something here, say, it does not have to be the case, right? Because see, we only have 2 parameters, alpha and beta, and there are 3 conditions, right? So three qualities should be satisfied. and it should be done only by manipulating with two parameters. It doesn't have to happen. Okay, that's right. Okay, now let's see. While we're at mathematical, maybe we can do some more calculations. Yeah, so let's talk more about the solution of equation of system of linear equations. So from the point of view of linear combinations, we can say that if A is a matrix and then it's A dot X is equal to B, right? So this system of linear equations has a solution, right? Or we can say that it has a solution. It can be one solution, or it can be infinitely many solutions, if and only if vector B, right, can be represented as a linear combination of columns of A. So this is just another way to say that, well, yeah, the way you're going to do it is like this, right? So say we have a matrix A, we're going to put it as in general filled by some entries, right? So J1 to say 4, 5. So this is, let's say this is matrix A, which is 3 by 5, like this. Sorry, comment. Now that's better, right? So it's yeah, right. And the say X is the free vector. I would say X1, X2, oops. X2, X3. So, and then if you say that this is equal to the vector B, with components B1, B2, B3, it's equivalent to say that this vector B on the right hand side, actually, sorry, X should be a 5 vector. I see something wrong. Otherwise, you cannot multiply. Now, you can rewrite this this relationship as follows. I can say that there's a vector A1, which is a vector which has components A11, A21, and A31, and so on. So A2 will have components A2, A1, 1, 2, 2, 2, 3, 2, and so on. So then this equation can be also rewritten as follows: that A1 times X1 plus and so on, plus a 5x5 is equal to vector b. So in other words, there should be a linear combination. There must exist coefficient x1 to x5, such that the linear combination of vectors, of common vectors of matrix A with coefficients to x1 to x5 is equal to b. So let's try to solve the following problem. So say you were given some matrix A, and let me take a smaller one. Let's take my matrix. Like this. So let's take for A matrix like this: 1, 1, 3, 4, minus 4, 2, minus 6, minus 3, minus 2, minus 7. So that's matrix A. X now is x is x1, x2, x3, and then we're asking ourselves what values of b. So this is A, b is this, and x is as usual, so it's x1, x2, x3. And the equation is ax equals b. The question: what values 1, b2, b3, the system the system is consistent. The system has a solution. Right. So in other words, we'll try to solve this system of linear equations at all possible values of b1, b2, and b3, and we'll identify the subspace of parameters b1, b2, and b3 where it's possible to do. Okay. Any questions? So, and we'll do it by working with augmented matrix. So we'll put matrix A on the left, and we put b1, b2, b3 on the right. Now, let's do something that we know how to do very well. So let's reduce this matrix to the let's transform this matrix to the reduced echelon form. What shall we do? So Sophie knows, Iris also knows, so we can, if you want, we can take a couple of minutes and do these calculations on our own, and then we compare the results. Is the question clear?
Yes, yes.
Sure. So first let's reduce it to the upper echelon form, and then you should give me the condition on b1, b2, and b3 when the solution exists.
Okay.
And then you can either tell it to me or send it to me as a chat message.
So what we do now?
Reducing this matrix to the echelon form.
Okay.
Do you have a pen and paper?
I have.
How about Sophie?
I have it.
Good. Awesome.
Should get the reduced echelon form or just the echelon form?
Yeah, that's right. Echelon form, but now keep in mind that B1 and B2 and B3 are some arbitrary.
So there, I think there's no solution. Is that right?
You can tell me the matrix. What's the first?
Nope. 1, 3, 4, 1, 0, 16.
1, 41. Next word.
0, 16. 10. 4B1 plus B2.
The connection is not well. Can you type in chat or you just say again the second row? So I don't think it's 16, it's 14, right? Because if you multiply it by 4, you get 12 plus 2, so that's 14. What's the next number? Okay, so
10.
Sophie says 10.
it's 10, right? Okay. And what will be here?
4B1 plus B2.
So 0, what's here?
Seven and 5.
7, okay, 5. And what? And then the bottom?
3B1 plus B2.
Yep, 3B1. Good. So that's echelon form. Now let's make it to the reduced echelon form. In fact, yeah, so it's not fully, yeah, so it's still not the full, yeah, so that's how it works. So you basically, you did the first pivot column, right? But we can still do something. There's next pivot here, right? We can do something about the two rows on the bottom, row 2 and row 3.
Multiply the second row by minus 0.5 and add to the third row.
Or multiply the third row by -2. Yeah, that's right. So yeah, if you do that, you'll get what's that? So yeah, so
0,
0, 0, and then this one will be what? So
yes.
that minus 1/2 minus 1/2 of P2 plus 4B1, and this can be simplified, right? So this is what it's this, right? B1 minus B2 plus B3. B2 half by B3. Right? Good, good, good job. Now, how do you answer the question in the problem? So, for which values of B1 between B1 between B3, the system has a solution? So, Iris, remember we talked about it earlier.
So no solution?
So we need to find a condition under which condition the system of equations has a solution.
So we should make a matrix in the equation now.
Yeah, we should make it to 0, right? So,
okay.
So the reason, because otherwise there is no solution. Otherwise we have x3 equals this. So it could 0. Otherwise we have 0 equals this number. So the only consistent, the only consistency check is when this is equal to 0. Right. So you can see that if we think of the, yes, in other words, B1 between B3 are bound by this linear relation. Right? Okay. We use the theorem that we have proven before. Okay. Now let's now talk about a particular example when vector b is equal to 0. Before we go. So now in space of B1, B2, B3, this is a plane, right? So you can, it will be a two-dimensional plane that is described by this linear plane. So okay, I'm going to repeat some of that tomorrow. Okay, and for now, I think the last story for today, we'll look at the equations of the form AX equals 0. What X is a vector. And A is a matrix. So for example, the solution of this equation. Okay. So that here we have 0, 0, and 0. Now, and we're asking ourselves, when does this equation have a non-trivial solution? So first of all, this equation is called homogeneous. Let's call it wrongly. as opposed to the inhomogeneous equation, where instead of zero, we have b. So this is called homogeneous equation, and this is called inhomogeneous. Ax equals to p. But first, let's talk about homogeneous equation. So now, so we have, in terms of vector analysis, we're saying that in terms of vectors, the linear combination of vectors formed by columns of matrix A is equal to 0, right? So can you tell me immediately what is, for which linear combination, for which values of coefficients x1 through x5, this will always be true? So can we always satisfy this identity? Can we always satisfy this relation? To which values do we need to put x1, x2, x3, x4, and x5 so that this combination will be equal to 0?
Let all the x become 0.
Yeah, absolutely. Yeah. So, and as we talked about earlier, this is so-called trivial linear combination, right? So it's always true for the trivial linear combination, which means that's x1 equals and so on equals x5 equals to 0. Okay, but that's sort of not interesting. The solution always exists, right? Basically, that means that your vector x is a 0 vector, and then multiplication by matrix on any 0 vector will always give you 0, right? What is less than trivial, if there is a non-trivial linear combination, that's so. Right? So question is, can we find a non-trivial one? So at least one of those x's is non-zero. Will that be possible? Okay, and then turns out that it is possible if the system has at least one free variable. So here's the statement. So the homogeneous equation Ax equals 0 has a non-trivial solution, or if and only if. So there's a symbol. So this if stands for if and only if. The equation has at least one free variable. Remember, in the first example we did today, we had the echelon form of the matrix, and then those coefficients, those x's that corresponded to non-pivot columns, they could be made a free variable. They could be made free variables. So I think let's look at the example, and then it will be the last thing for today. So take the table matrix. So let's take this matrix. I have it in the notes. 3, 5, minus 4. Minus 3, minus 2, 4. And then it's 6, 1, minus 8. Right, so That's the matrix. That's matrix A. And the corresponding system of equations. Well, by now we should know this, right? So it's this. It's the this times x1, x2, x3. Is equal to 0. So it's this is equal to 0, this is equal to 0, this is equal to 0. That's the system of equations that we're solving, right? So because the right column is equal to 0, we need to write the augmented matrix for the solution, where the right column is just 0. Right, and we need to reduce it to the echelon form, right? So you can do it as a. So I think unfortunately we have to go right now, but I need to switch the Zoom link to the next class. So you can do it at home. We can read about this in the book. So we need to reduce this matrix to the echelon form and find the free variable. Well, and solve the system of equations. Okay.
Okay.
Good. That's it for today. So tomorrow I'll lecture a little bit more, and then we can have some more for discussion. So we will hopefully finish the first chapter. So we are now at chapter 1.5. We have a couple of more sections to talk about. Okay, great. Thanks for joining. So it was that's it for today. See you tomorrow. Thanks. Bye.
Bye.
Bye.